kinetics of particles. Force analysis of dynamic systems, as I mentioned in the previous class, is purely based on Newton's laws at this level. So the Newtonian mechanics that we are going to apply for that purpose. But if you are interested in this work, then for certain fields of specializations, you will learn more advanced stuff like Lagrangian mechanics and Hamiltonian mechanics and things like that. But at the moment, we focus on Newton's laws. So Newtonian mechanics, so that is based on Newton's laws. So the Newton's first law, everybody knows, that is about the momentum of a particle is constant when it is free of external forces. So momentum will be zero if it is at rest, and the momentum will be constant when something is moving at a constant speed. So momentum is mass into velocity. Newton's second law says rate of change of momentum is proportional to the external force, net external force acting upon it. So that is F equals ma. And the third law, of course, everybody knows, it is about the force equilibrium. That is, each object exerts an equal and opposite forces for equilibrium. Now, when it comes to general discussion about the motion, if any object is not constrained or has been given the full freedom to move in the space, we call it is free motion. So the total freedom is provided to move as the object would wish to. So, so that kind of motion is called free motion. But in real engineering applications, we hardly find free motions because we don't want any objects in most of the cases may be a part of a robot, maybe a part of an automobile or any other machine for that matter. So we want these various components of these machines to move in a desired way, not just moving one place to another place freely. So we want to get something useful work out of that motion. So that is the whole point of engineering. So the free motion is more or less very general type of motion where it has given the total freedom to move in the space. So usually for a particle motion, such movements can be defined using three independent variables, that is x direction, y directional variable, and z directional variable. So these three variables will be adequate to define the velocity, acceleration, position, whatever you want, if it is completely given the freedom to move as it is. We need three variables to define the motion, and we call that situation as 3 degrees of freedom. 3 degrees of freedom. That means the motion needs 3 variables are needed to define the motion. So that is free motion. So that is only for particles, but if it is a rigid body, then of course, in addition to just moving from one point to another point, rigid bodies will also rotate in the space. Therefore, we have to consider the rotations about x-axis, rotation about y-axis, and rotation about z-axis. So those rotations are also required. Therefore, free motion of a rigid body will have 6 degrees of freedom. You need 6 variables to completely define the motion, if it is a rigid body. But if it is a particle, of course, there is no rotations in particles. Therefore, rotational dimensions we don't have to consider, variables we don't have to consider. So 3 dimensions will be adequate. So a simple example is a projectile motion. But as I said earlier, now in most engineering applications, we are interested in constrained motion because our machines, we want to work in the way that we want. And those need to do certain tasks. Accordingly, we can't simply let the parts fly all around in the space, but we need them to operate in a certain required way. So such defined definition of a certain motion pattern using certain restrictions is called constrained motion. Constrained motion. So in other words, in more technical words, by means of constrained motion, what we do is we reduce the degrees of freedoms of the system. That means we constrain certain degrees of freedoms and we do not let the object to enjoy certain degrees of freedoms. Therefore, it will become a reduced number of degrees of freedoms. For example, if you consider motion along a predefined surface, something moving along a table or something like that, 2D space, that will have only 2 degrees of freedom because z directional motion is restricted. We are not, we do not allow that object to jump out of the table, for example. And if it is a object which is moving along a curve, so the variable that may need to define the path will be the s, the path traced by the object on the curve. So that in that case, it will be a 1 degree of freedom system. So maximum it can have 3 degrees of freedoms, but in constrained motion, we restrict certain degrees of freedoms, certain movements. The forces acting on this constrained motion, of course, in order to move a particle from one point to another point, you will have to apply external force, unless or otherwise it moves at a constant velocity along a straight line. So there can be external forces applied on it just to provide the motion, just like the weight of the object and any other friction force or anything like that. And then the constraint forces, just to make sure that object moves only along a certain predefined path, we have to restrict definite degrees of freedoms. Just to restrict the degrees of freedoms, we'll have to apply a force. We can't change any movements without applying force. So forces that provide that constrained motion are called constraint forces. So for example, if you want this object to be slide on this smooth curved path, then this is a constrained motion. The motion is constrained to move along this curved path. And if that is the case, then there has to be a force applied on this. So what is that force? Normal reaction. So the constraint force comes from the normal reaction. But it's not normal force to weight. Normal force to weight, of course, if it is a static, I'll come to that with a small example. If it is a static object, of course, it is the reaction to the weight. But if it is a dynamic object, that is something moving with an acceleration in particular, then there are dynamic forces. Because the mass and acceleration combines and create a force, which is the inertia force. So not only the weight, but also dynamic forces need to be considered, and those dynamic forces need to be constrained. Whenever you have this something moving along a path, the reaction is the constraint force, and the reaction is always perpendicular to the contact surface. Perpendicular to the contact surface. Therefore, in this case, normal reaction is along the radial direction towards the center because it is a circular path, and the weight is the applied force that is downwards. And N is constraint force, and this is a single degree of freedom. So one parameter is enough to define the kinematics of this. So there are two force components. Applied force and the constraint force, N and R. And then we can use Newton's second law to find the dynamic forces. Again, remember, we are analyzing dynamic forces, not static forces. Therefore, the forces coming due to acceleration need to be considered. So, if it is a motion along a curved path, like what we just looked at, we could use polar coordinates, and these polar coordinates will become tangential and normal coordinates if it is a circular path, because the theta direction becomes tangential and r direction becomes radial or the normal in the case of circular curve. And then, of course, these are the two unit vectors that we use to define these quantities. And we can apply Newton's second law in the normal direction and tangential direction. So in the normal direction, of course, you get all the forces, reaction as well as applied force, again, depend on the direction of applied force. But in the normal the tangential direction, of course, the reactions won't come in the tangential direction because reaction is always in the normal direction. So the acceleration is in the normal direction, acceleration is r phi, in this case angle is given as phi, r phi dot square, and the tangential directional acceleration will be r phi double. So application of Newton laws in these two mutually perpendicular directions is what we need to do. So if you do that, you will get these simple relationships in the normal direction. Newton law in the normal direction and Newton's law in the second law in the tangential direction. And that gives you a situation like this. And if you assume W is mg, the weight, then you can replace W with mg. And at the same time, the parameter that we don't know in this particular case is the speed or the acceleration, angular velocity or the angular acceleration. So we can find those quantities if you have boundary conditions given. For example, acceleration, angular acceleration, we can represent using this one, phi dot over dt, but d phi can be included here. And this is phi dot, in fact, d phi of dt. So, so with that, of course, if you cross multiply it and replace W with mg, you will get to this point, simplification. And then you can apply the boundary condition or the initial condition where you start from phi equal to 0 and 0 velocity when t equals to 0. With that initial conditions, you can integrate this relationship and you can find the value for phi dot, angular velocity, and also the velocity will be r phi dot. So those quantities can be found. And obviously, velocity will become maximum when sine theta or sine phi, in this case, sine psi becomes maximum. And that will happen at the bottom where phi psi becomes 90 degrees. And at the same time, if you look at the normal force or the constraint force N, using the first equation, this one, you substitute W equals mg and acceleration, of course, using this relationship. Then you will simplify this to N equals 3W sine psi. So mg is W. So 3W sine psi is what you get as the normal force. And you can see now this W is the weight, and due to these acceleration forces, that weight has been threefolded due to acceleration forces. For example, psi equals 1, psi equals 90 degrees, then N becomes 3W. N becomes 3W. So that is the effect of the acceleration. So the inertia forces play a significant role in the kinetics of moving objects. So if you neglect this inertia effect for some reason, you will be neglecting two-thirds of the force. So that is significant component, and that will result to some failure of components, breaking of components, and things like that. So if it is static situation, this normal reaction at the bottom is W, but due to inertia forces, so the acceleration effects, it has been multiplied by 3. So that is the severity of the inertia forces, and always we need to consider these inertia forces in our analysis when it comes to dynamic problem analysis. Okay, so there is a problem here. Example 1. I'll give you a couple of minutes for you to think about it. Can the weight influence this motion as it is? No. Why? Because it is horizontal plane. Yeah, that is very important. So we'll have to read the problem clearly. So if it is going in a vertical plane, of course, the weight makes the difference. But if it is horizontal orientation, weight doesn't make any influence on the motion. And at the same time, this problem says, now of course the constraint force is there, that is the normal reaction. And in addition to that, this problem says find the force acting on the mass if it moves with a constant velocity v0. Now this one is moving away at a constant velocity. That is what it says. This is moving away at a constant velocity. So now we know that when you turn this plate, then definitely there is a centrifugal acceleration. That acceleration will try to move this object with an acceleration. So that it cannot be a horizontal, it cannot be a constant velocity under normal circumstances. The object has an acceleration, so the velocity tends to increase as it turns. But in this particular problem, it says it's going at a constant velocity. So how can that be? So there has to be a certain force. So either friction force or any other way, you'll have to apply a force in the opposite direction to the direction of motion, so that the velocity could be maintained at a constant value. Otherwise, definitely, it will be going at going with an increasing velocity due to the acceleration. So those things you need to clearly understand. So if you omit some components, your answer will be wrong. So that is where the problem is most of the time when it comes to examination questions and things like that. Things look very simple and easy, but certain fundamental things you miss when you work out problems. In this particular problem, there is no information given about that force, but when it comes to real implementation, of course, we'll have to apply a force in the opposite direction of the motion to maintain the velocity constant. So in this particular instance, that force component is not described, what kind of, whether it is friction or whether it is a traction force or whether it comes from a spring or anything like that was not given. So we don't have to worry too much about the type of force applied on it, but there has to be a force component. So that is what is more important at this point. So the forces will be obviously it has to be downwards, but we can represent it opposite direction and we'll get a negative value if we are wrong. And there are two force components and two directions as usual we can define, and we can write down equations by applying Newton's second law in the two mutually perpendicular directions. And the acceleration in general terms, we know that we obtain this equation, and because this is a problem where the value of r is not constant, so it's not going in a circular path, even though it is a circular plate. Even though the plate is circular, object path is not circular because r is changing. So But since it is going at a constant angular velocity, psi double dot will be 0 and r dot is constant and r double dot will be 0. So r dot is v naught, which is constant, and this one will also become 0. Therefore, the acceleration in the r direction will be minus r omega naught squared, and in the theta direction, or the psi direction in this case, is the Coriolis acceleration, which is 2 v naught into omega naught. So those are the accelerations. So if you substitute these values over here and here, you will be able to find out the value of Fr and value of N1. And Fr, obviously, we knew that it has to be minus because the force has to be downwards in order to maintain the constant velocity. And N1, the reaction force, is coming due to this Coriolis acceleration. So that is about applying Newton laws to work out the problems subjected to constrained motion. Now, if you look at the force component, applied force components that we commonly find in engineering applications, one common component that we find in mechanical component is a spring. And for the moment, we can assume the springs are linear springs. And spring force is always, spring tries to get back when you stretch a spring or when you compress a spring, depending upon the type of spring. There are two types, compressive springs and tensile springs. Tensile springs we use to stretch, and compressive springs we use to compress. So whatever it is, spring always tries to get back to its original position. Therefore, the force it will be always opposite to the force that you apply. When you apply a force, spring tries to get back. So the spring force is in the opposite direction. So if it is a linear spring, we can apply the simple Hooke's law and find out the force as proportional to the amount of displacement that you impart on it. So that is Fs equals a constant into x. This particular constant is called usually the spring constant or the stiffness of the spring. To correctly find the forces, it is very much important to identify the right directions. So if it is a circular curve, for example, like in this case, this object is moving along a circular curve, direction of normal reaction or the normal force, we know that goes through the center of the circle. So we can easily find this direction of the normal force. But the problem comes when the path is not a circle. Or in other words, always the path of the movement of a particle will not be a circle. When the particle is not moving along a circle, then the problem comes of how to find the direction of the normal reaction or normal force. Now, for example, if you look at a limacon, a curve like this, which is defined by r equals 2 plus cos theta, 2 plus cos theta, the r is this one and theta is this. So this is not a circular shape or circular curve. This is not a circular curve. Then the normal reaction or the normal force is of course normal to the tangent drawn at this point to the curve, but we don't know what that direction is. To find the direction of the normal force component or the reaction, we could look at the slope of a polar curve. That is, if you draw a tangent to any curve at a particular point, P in this case, then if this angle is beta, we know that the slope of this tangent at point P, dy by dx, is tan beta. Now we know that in polar notation, P a point with coordinates r theta, where r is this distance, the length from the origin, and theta is the rotation in counterclockwise direction.
So x equals r cos theta and y equals r sine theta. So dy over dx we could find in terms of dy over d theta multiplied by d theta over dx. And we can find dy over d theta by differentiating this y equals r sine theta. And similarly, dx over d theta also we can find. And then when you divide dy over d theta by dx over d theta, we will be able to find dy over dx. So dx over d theta is the derivation of this with respect to theta. You can find it. And dy over d theta also you can find using this. And then if you divide these two, then you will be able to get dy over dx. And that is over here. And you can simplify this dy over dx by dividing both the denominator and the numerator by cos theta. So you get here. And then if you multiply the denominator and the numerator by d theta over dr, then you will come here. If you draw a horizontal line from P, this angle is theta, the same angle here. And if you define this angle as psi, then beta becomes theta plus psi. That means dy by dx is tan theta plus psi. And you can expand this using tan equation, so that our dy by dx becomes tan psi plus tan theta divided by 1 minus tan psi into tan theta. And if you compare this relationship with the one that we obtained earlier, you can see instead of tan psi, over here what we have is r d theta over dr. The tan theta remains the same in both equations. Here you have tan psi term. Instead of that, what you have here is r d theta over dr. And here you have a tan psi term, and the same term appears here. So accordingly, you can compare these two equations and conclude that tan psi equals r d theta over dr. So using this relationship, we will be able to find the angle psi. And if you can find this angle psi, then you should be able to find the normal direction. Perhaps you have done this simplification under calculus somewhere down the track, but I just recall this because this is a very important relationship for us. Tan psi equals r d theta over dr, particularly when it comes to locating forces under constrained motion when particles move in complex curves other than circles or straight lines.
And remember, if you get a negative value for this tan psi or the psi, when you simplify this one, then you will have to consider, you can recall from your notes, this psi will be this angle. Psi will be this angle if you get a minus value for the value of psi in this case. Otherwise, if the value is positive, then as shown here, you would take it. So this information is important when the constrained path is not a well-known path like a circle or straight line.